All right, so what we've done so far is that we've actually understood and reviewed the single stage amplifiers, right? I mean, we've looked at, single transistor stages, really. And we've looked at a couple of them with more transistors, and we'll talk about it. But what we did first was that we understood there's three basic configurations, right? That where in the case of a MOSFET would be common source, common drain, or also known as source follower, and the common gate. And we saw that each one of them has certain properties. These are the most basic building blocks. And then what we did, for example, we saw in the case of a common source, you have a reasonably high input impedance. You have, depending on what kind of the load you use, you can have a high impedance output, a high impedance output, because essentially the output impedance, what you see is what you see looking into the drain, or in the case of a common emitter, you're looking into the collector. So that's where the terminal with the highest resistance. And in 2 out of these 3 configurations, the output is taken out of the collector. So those are the ones that give you the high output impedance in principle. Now, of course, if you take that intrinsic high output impedance and put it in parallel with the low impedance, of course, the overall impedance is going to be low. But so when we talk about the output impedance, we're talking about the intrinsic, what you see looking in the transistor. So remember, this transistor roughly, looking into the source, you see Rm, or looking into the emitter, you see Rm. Looking into the gate, now, or base, this is where it's going to be different. So in bipolar, because you have the current, you have the R pi, which is beta times the Rm. In the MOSFET, you have basically infinity for classic MOSFET, because there's no DC current flowing. But that also means that that terminal cannot carry current. So you really can't take an output out of that. You can't make the gate your output because there's no current handling capability, right? And if you think about it, then there's the drain or the collector, which has the RO, due to the early effect or channel length modulation or things of that sort, in general, an arbitrary combination. So the common source and common base, common source and common gate, or the common emitter and common base, both of them take the output from the collector or the drain, right? Now, the difference is that really the polarity of the input that's applied, but that implies that you're applying your input to a terminal that's low impedance in principle, Rm, or a high impedance, higher impedance one, like R pi, or in the case of MOSFET, infinity. And the third kind of like combination was basically the common collector or common drain, where basically your input was applied to your gate or base, which had relatively high impedance. Now, what your output this time is taken from the source or the emitter. Now, the output is now taken from the terminal that has low impedance, right? So the output has to be taken out of out of the terminal 1 or terminal 2 in the case of any arbitrary 3-terminal device. Those are the ones that can carry current. Generally, you don't take output out of base or gate because there's no current generation or current handling capability in there. And that basically leaves these 3 combinations. So these were the basic 3 combinations. And then what we saw is that we looked at essentially what were some of the 2-stage transistor stages. So what we did, for example, we looked at Cascode as an example of a way of increasing the output resistance. We did the analysis. We saw that in the case of a bipolar transistor, the maximum output resistance that you can achieve with something like that was beta RO. And in the MOSFET, we saw that it kept constantly getting multiplied by the intrinsic gain of the stage. So for example, if it was RO, then when you had a Cascode, you had the GMRO times that, and then kept going up. Of course, there are some practical limitations. So these were some examples of two transistor stages. So today, we'll talk about more 2 transistor stages. And of course, next day we'll talk about 3 transistor stages, 4 transistor stages. No, just so 2 transistor stages have interesting properties, and they will become more actually become more of building blocks for us too. So we talked about Cascode first, right? I mean, Cascode was one of the things we talked about. And so let's review Cascode for a second, right? I mean, so go back to Cascode as another example of a 2 transistor stage. Now, what do we mean by 2 transistor stage? The Cascode, if you remember, was a stage where you can have, for example, if you do it in a MOSFET implementation, and by the way, we'll switch back and forth between MOSFET and bipolar constantly. So you should be able to be comfortable with those, or even ATDs, arbitrary 3-terminal devices. So the concept is There's a lot of similarities in the content. So you have something like this. You have an RD here. You had two transistors, W over L's, let's say 1 and W2 over L2 in general. We can keep them the same for now, assume that they're the same. And then the input is applied here, and this is the output. And this is V bias. Now, for the time being, for many of these stages, you will for the next lecture or two, well, this lecture and maybe next, you may see a lot of these. And afterwards, you may see a lot of these like V bias. Right? At this point, it means that somehow we are maintaining a constant voltage here, or mostly constant voltage, which essentially means that you can think about it as a voltage source. We'll have extensive discussions about how these things are generated. And we'll make it more sophisticated as we go through. So, but for now, let's just not worry about that. And we'll come back to it later. So in the Cascode, we had two stages, and the input was applied here and the output was applied there. So if you wanted to analyze it, what you could say, again, we will try to kind of think about these as doing the small signal model on this thing. So what we really mean is that this Vin has two parts. It has a DC part that keeps the transistor biased, and it has an AC part, which we'll show at lowercase Vn. And that would, so what we know, if the transistor is in the pinch-off region, which is a condition that needs to be satisfied in general, so that's the first thing we check. So if you are in pinch-off, we know that this is going to generate a current, a small signal perturbation current of GMVN, right, here. Now, we know that this current is going to be reflected here at low frequencies, right? Because we know that the drain and source currents of a MOSFET are essentially the same, because the gate current is, in the classical model, 0. So this current is directly appears here, these fluctuations will directly appear here. So this current is being pulled out of this node. Another way to think about it is that you can say, I have no source here. So this is another way to think about it. You can say, I've nulled this. So from an AC perspective, or from DC perspective, this is just a fixed voltage. And from an AC perspective, it's ground. And then there's a current source here of the value GMVN being pulled out of this node, right? I'm basically doing essentially a Norton equivalent, if you think about it, with this terminal being the output terminal and ground. I'm saying that this whole thing, if I remove this source, I can replace it with a Norton current source here that's being pulled out of this thing. So when I draw these pictures, that's what I mean, right? So I'm going to erase this now, but you can think about it that way if it bothers you, what I'm doing. So this red stuff means that there's a current source being pulled out of it, and you can ignore the effect of this guy then, because that would replace this. Now, if I want to know what's the voltage on that node, how do we do that? Well, if I want to know what's the voltage on a given node, if I know that there's a current being injected into it or being pulled out of it, what do I need to know? What else do I need to know? The resistance, right, to apply Ohm's law. So I need to know what's the total resistance on this node, because that current source was being pulled out of it. Right? So what is the total resistance on that node? It is the parallel combination of what you see looking up and what you see looking down. What you see looking up, basically when I say looking up, it means that looking up to the ground, to the AC ground. All of this stuff is a small signal. So this is RD, right? From a small signal perspective, this terminal is what? Is a ground. So this is an RD to ground. Now, what is the resistance looking down here? Again, to evaluate that, I should null my independent source, right? I'm doing a Norton equivalent, if you want to think about it that way. Now, I'm shorting this, and I'm looking into here, and I want to see what the resistance is. And we've calculated this resistance before, right? We know, so let's call this M2 and M1. This is basically RO1 times 1 plus GM2 RO2, which, again, it's better to, I actually prefer to write it like, unless this number is very small, I would just write it as RO1 GM2 RO2. Unless this number is really like 2 or 3, this 1 doesn't matter. Basically, what is that number? What is that GM2RO2? What is GM2RO2? What is this thing? This thing or that thing? Isn't it the maximum intrinsic gain of this transistor? So that's basically AV max 2. A max 2. right? So you can see that the output resistance of this guy, which is what you would have seen looking down here, is multiplied by the maximum intrinsic gain of this guy because of this common gate operation. So that was the essence of Cascode, right? We've seen this before. And we exploited this last time to make stages with higher gain. We said if you needed higher gain, you need to, the only way, so your drive is fixed. Let's say you have a given drive, right, which is this GM. Now for a given amount of drive, you want to maximize the gain. What do you need to do? You need to maximize that resistance on that node, this total resistance, which is the parallel combination of that and that. Now, if this is small, then this will not matter. So obviously, we have to make that large. And we saw the way to make it large, for example, was to put another Cascode here, right, as the load, which represents a similar kind of load. So the idea was that if you wanted to really maximize the gain, we went to something that looked like this. And we did this last time. So I'm just reviewing this for you quickly. So you use two p-FETs, or if you were doing bipolars, you would use PNPs, or use p-type devices in the case of an arbitrary transistor or arbitrary three-terminal device. And then you have something like, so this is VB1, VB2, VB3. These are bias voltages. These are fixed voltages. This is your Vin. And again, your output is taken from here, Vout. And if all these devices remain in pinch-off, which is the requirement for this model, the small signal model that we use to hold. If you're in a triode region, then you basically have a resistor model for the channel, which we have also derived before. So if you are in pinch-off, what we see here, so let's call this M1, M2, M3, and M4. So again, same deal. The same calculation. So you say this is Vin. So this is going to be GMVin, this fluctuations here, small signal variations, which will be directly appear here because the current gain from the source to drain is 1 for a MOSFET. And if it were bipolar, what would this be? For example, if this was a BJT, what would this number be? Alpha times that, right? So if you had a BJT, it would get multiplied by alpha. Now, and then this is again same deal. The only difference really between these two is that the output resistance looking down is still the same thing. So we can write it roughly as RO1 GM2 RO2. RO1 GM1 RO2. And then the question is, what is the resistance looking up? Now it's not RD because we've replaced RD with something else, right? What is it? Well, it's a similar thing, right? It's a similar Cascode. It's just upside down, right? Because the source of this transistor is AC ground, right? It's like the Cascode except for the fact that its input is not changing. But it's the same deal. So what do you see looking into here? You see RO4. And looking into here, you see basically RO4 times GM3 RO3. It gets multiplied at the maximum intrinsic gain of this stage as then the same thing as this stage. I'm missing an arrow here. Okay.
Different GMs for the small signal current, right?
Okay, so you're saying that is this GM different from that GM? Is that?
Also on the right.
And this one?
Same diagram for the red.
For the red. No, so this would be GM1. Right? Because this is the guy that's converting this from. Yeah, it's a good question. So it's converting this Vin to a current here. So this M1 is the one that's doing that one. So it's really GM1. Now, again, are these GMs the same or different? Well, it depends what the currents are, right? So in a case of a bipolar transistor, let's say, for the sake of if this was done with bipolars, so if these were NPNs and these were PNPs, and if they were sharing the same current more or less, and if you ignore the alpha, assume alpha is 1 or beta is infinity, then all of them share the same current. In the case of a bipolar, the transconductance is determined by what? It's simply IC divided by VT. So they will all have the same GM, more or less, to an alpha. Right? But, sure. But in a MOSFET, that's not necessarily the case because they can have different W over Ls. And you can see that there are more knobs in MOSFET design. because W and Ls are parameters of the design. And you know that in both expressions that we had for the GM of the MOSFET, both in terms of current, which was that square root of 2 mu n C ox W over L ID, or in the voltage format, which is basically mu n C ox W over L VGS minus VT, both of them had W over L in them. So by changing the W over L, keeping everything else, even if the current is the same, you can change the GM. So this GM can be different from the GM of the other one. So this is still GM1. Right? So these GMs can be different in a MOSFET. I mean, in bipolar, they are also different a little bit because of the alpha, but yeah, what's an alpha between friends? Right? So here's what you have as the basic transistors. Now, it seems that it's actually helping, because now what is my gain? If I ask you what is your gain, I want you to be able to have intuition about this gain. You need to be able to give me not super precise expression, but you can say it's roughly this. So what is it roughly in terms of expressions that we have? Anyone who wants to go for it? What is the gain? The voltage gain from here to there. Isn't it this current? The output voltage is going to be this current times the total resistance you see on this node, right? So what is the total resistance you see on this node? It's this resistance in parallel with this resistance, right? The resistance looking up in parallel with the resistance looking down. And what is the drive? It's GM. So it should not be surprising if we say AV, defined as VO over VN, is going to be negative, and that's because the current is being pulled out of this node. Negative GM. Okay, so let's make this. Negative GM1 times the parallel combination of these two terms, RO1, GM1, RO2, in parallel with RO4, GM3, RO3. Right? Does it make sense? Anything that kind of troubles you or bothers you? Yes?
Why did GM2 from the first problem become the GM1?
Because I made a mistake. This should be GM2. Thank you. See? Because that should be GM2. Thank you for that correction. It was that's a simple explanation. Yes. Thanks. All right. Very good. So that's what you see, right? That's what you will get. Now, this thing can be large if the maximum intrinsic gain is large, so you basically increase it. And we saw that you can actually do a triple cascode, and you can get to ridiculously large numbers. You can even think about doing quad cascode. And at some point, we saw that if the numbers become too large, it means that essentially your model is starting to fail you. Because there are other things you're not modeling. There are other resistances you're not modeling, the leakage currents of the diodes and things of that sort. So don't get carried away with this. But you will see sometimes triple cascodes in MOSFETs. I don't think I've seen many practical circuits with quad cascodes, but just triple cascode I've seen. And there may be cases where people use quad cascode. If you think about it, probably I may remember something. But anyway, that doesn't matter. The key thing is that it matters. We built this cascode. We did this last time too. But now the question is that what is the problem if you wanted to cascode more and more of these things? Let's say you wanted to do a triple cascode to get a lot of gain. What would be a practical problem? Well, think about it. What's happening to the process technologies? How are we making them faster? The scaling, which is one of the bases of the Moore's law, right? You're in the Moore's lab. Same Moore. So with Moore's law, what's the limiting factor? What is happening when you scale the transistors? You're trying to make it smaller, right? We talked about this when we were talking about device physics. And when we make the transistor smaller, what happens to the voltages? We are shrinking the depletion regions, but you have to also shrink the voltages to make sure that you don't exceed the critical voltages. So what happens is that the supply voltages are shrinking. And as a result, you remember, we said all bets are off as far as this model is concerned if these transistors are not in the pinch-off region. And to be in the pinch-off region, you need to maintain a minimum VDS, right? Which has to be greater than VGS minus VT on every single one of them. So there's a little bit of voltage you need to maintain here, a little bit of voltage you need to maintain here, you need to maintain here, you need to maintain here, right? So let's call this, for the sake of argument, let's call this voltage, this DC drop you need to maintain is V1, and then DC drop you need to maintain here V2. Well, I drew it in the wrong place, really. It should be, it's very crowded here, but it's okay. So it's called V1 and V2, right? So this is the DC you need to maintain here. And at some point, what happens? So let's say you are at a low voltage. So let's say this V1 you need to maintain. Let's just pick a number. It's like 0.3 volts, and this is 0.3 volts, and your supply voltage is 1 volt. What's the problem? What's the problem? Can you think of a problem?
You run out of supply voltage at the top.
Right. So there's only a 0.4. If this is 0.3 and 0.3 and this is 1, there's only 0.4 volt at most in the middle that I can operate. This can fluctuate up and down. It can move up and down only 0.4 volts before one of these things goes into triode region. So your active range is reduced. This is basically called headroom, right? Because if these are the rails, it's like a room, just like you're lowering the ceiling, so you're more crunched in between. Now, what happens here is that, okay, so that's a problem. How do we solve this problem? Can we think of a solution to this problem? Well, this concept, this even applies here, if you think about it. Because now you need more headroom for something like this as opposed to a single transistor. So how can this evolve into something that solves this problem? Yeah. Folded cascode, right? So what do we mean by folded cascode? The challenge is that the reason you're going up in voltage is that you need to maintain a positive voltage between drain source and drain source of this guy. Why do we need to maintain a positive voltage? Because these are N-type devices. Now, but for P-type, you maintain a negative voltage between the drain and source, right? If you think about it. So this is the drain and this is the source. So the drain source is negative. And what's the definition of cascode? The cascode is not defined by the way you draw these things. It's defined by what terminal is connected to what terminal. The cascode really is a common source followed by a common gate. That's the definition of a cascode. Or a common emitter followed by a common base. Or in our ATD, common terminal 1 followed by common terminal 3. So regardless of that, we need to do that. But now if we get this guy as a PFET, we can actually make this reduce the voltage. So now, would this work? Can I do just if I draw something like this? Well, no problem. I'll make this a PFET. What's the problem with this picture? Or is there a problem with this picture? So I've made this into a PFET. Blindly. Well, remember, PFET. So PFET transistors is this? Well, not this way. Sorry. This way. Because it had to be a common source followed by a common gate, right? And common gate gets its input from the source. Does this work? No. Why not? Because the DC. If this were really a PFET. What happens is that the current needs to be flowing in this direction, the DC current. And for this guy, the DC current needs to flow in this direction. We're talking about DC currents. Maybe I should use a different color. So the DC current flowing this way, and the DC current is flowing this way for this guy. So obviously, you have a problem, right? You have two devices that are trying to pull current out of the same terminal, right? And then this is also a problem because now you're trying to push something into this guy. So this is going to try to go above VDD, which it can't. Because what happens if so you can say, well, what do you mean you can't do this? I can do whatever I want. I can take two transistors and connect them any way I want. And it's not going to be a black hole or something like that formed by doing that. So something's going to happen. Yes, that's true. Something's going to happen. What's going to happen if you connect them this way? What's going to happen is that the source and drain are going to switch. Because this is going to be at a higher voltage than this terminal. So since NMOS MOS transistors are essentially symmetrical, so what the correct drawing for this block diagram would be becomes this. And then when that happens, you look at it, it looks like this basically from here to there, there's not going to be much gain. Because from here to there, you had some gain because you had the basic active load with some resistance here. But then it basically becomes a stage that doesn't carry that much gain. So we wanted to have that. So it's clear. And this is not Cascode anymore, because Cascode by definition was a stage, a common source. So the drain of the first transistor should go into the source of the next transistor. Right? So what do? We have a problem. The problem is that they're trying to both draw current this way. So what do you need to do? You need to provide a source of current. Right? What is that source of current? Well, you can put a current source. So you can say, OK, I put some I bias here, and I drive current into this thing. Right? So now you have a DC supply of current that provides current to this thing. And if this were really an ideal current source, from an AC perspective, what you see looking here, looking down here, it's an open circuit, so it's not going to do anything. So if you indeed had an ideal current source, you would see that. Now, what if you well, we don't have an ideal current source. True. So what is a non-ideal current source? The non-ideal current source has some resistance here. And for it to be a reasonable current source, this resistance has to be reasonably large for it to be called a current source. So now, when you open circuit this one, you see this resistance. Now, is this resistance a big deal if it's a large resistance? What do you think? Do you think it's a big problem, small problem?
Depends on how large you can make it.
Well, OK, so let's say it's in. How do we make current sources? We haven't really formally talked about it, but we make it out of transistors too, right? Now, what's the defining characteristic of a current source? High impedance, right? So if I wanted to make it out of a transistor, then, if I wanted to make it out of a single transistor, which terminal of the transistor would be the output of the current source in your mind? The drain or the collector, right? The one with the highest impedance. So this is going to be the impedance. So it's going back to your question, which is a good question. So how high is this resistor? It's an RO. RO-ish, or maybe higher, if you can make better current sources, which we will make. Right? So this is an RO. Now, if this were an RO, would this be a problem? Here. Would this be a problem for this node? So to understand if it's a problem or not, we have to understand what the other resistances are first, right? What is the resistance you see here? This is another RO, so this could be significant, right? This is an RO-ish thing. This is an RO. Now, what do you see looking up? Looking into the source, what do you see? RM. So you have, on that node, you have 3 resistors in parallel, an RM, and an RO, and an RO. Would adding a second RO to this combination matter? If you have an RM parallel with an RO already? So let's say if this were bipolar, so you're talking about 25 ohms versus 100 kilo ohms. So if you have 25 ohms parallel with 100 kilo ohms, you add another 100 kilo ohms in parallel with it. It's still 25 ohms, right? Yes, no.
We said that the resistance looking up is RM, but does it make a difference that the current is flowing off?
OK, that's a great question. I'm glad you asked this. So she says, I said the resistance looking up here is RM, but does it matter which way the current is flowing? Well, remember, this is important to recognize. That small signal model is valid because it's a perturbation. It's valid for NMOS and PMOS. Actually, it's the same for an NMOS and PMOS. It looks the same because it's a perturbation model. It's a derivatives. Right? So it's a fluctuation of this current anyway.
So we can model it
The same way. I mean, the small signal model for this thing is exactly the same thing as that of the NMOS, which is very convenient. So you don't change your small signal model remains the same for PNP or NPN or NFET and PFET or N-type and P-type devices. Doesn't matter. The small signal model is the same. Because it's an incremental model. It's the fluctuations. If you do that derivation, basically you will see that there are 2 minus signs that cancel each other when you do the differentiation. So you will get exactly the same thing. And it makes sense because that resistance cannot become negative. Right? I mean, the basic resistance cannot become negative. So anyway, so this doesn't matter. So we take this and we redraw it in a more common fashion. And again, this is one of those things. A lot of things in circuit depends on how you draw it. If you draw it poorly, you can make it become unpleasantly difficult, which some people intentionally do. So now here's the same thing, right? The only difference here is that I also had to make another change to my R. Because if this resistor goes to VDD, then it can't sink current. Because remember, this is going to be, current is wants to go upward. And if this is VDD, it means that this voltage has to go above VDD, which in this kind of operation cannot. I mean, there are some circuits that you can design that push it up. But at this point, it can't. So it has to be referenced to ground. But from an AC perspective, it's not going to make any difference. So this is going to still be RD. So this is what we call folded cascode, right? And the idea of folded cascode is that now let's see what the voltages look like. So even we could make it a double folded cascode. So let's say if we were talking about singles for a second, if you were thinking about singles, the DC voltage across here was V1, and let's say here we had V2, right? Or the entire thing, let's say. This is V2. Now, instead, you have, so the total VDD here was basically V1 plus V2. So V1 plus V2 was VDD. Had to cover the entire VDD. Here, though, you have a V1 here and a V2 here. So this voltage, so what you have is that, according to this, V1 is equal to V2. But it can be smaller than what you get from the VDD. So you have more headroom this way. Now, this concept of the complementary devices, you see that we are using these complementary devices. We will see them more and more. It's very powerful if you have them at your disposal. In other words, when you have NMOS and PMOS, or NPN and PNP, it's quite useful, especially if they're somewhat symmetrical. By what we mean somewhat symmetrical is that one of them is not significantly worse than the other one. And sometimes this is the case, and sometimes it isn't. Now, whenever you have NMOS and PMOS, every stage has an inverted dual, right? You can flip it upside down. So if you start, for example, with a common source, let's say, RD, so this is a basic stage, right? We've talked about this, common source like that. I can always flip it upside down and use a PFET. So what we can do, the dual of this thing would be, or if we invert it, how would it look like? Well, I can use an PMP or PFET instead of an NFET, right? P-type device. So I'm going to use a P-type device. And now remember, for a P-type device, the source has to be at the highest potential. So we have a VDD here. Now, this would be my input, Vin. And the load now needs to be referenced to ground. So this is the inverted version, or upside down version of it. So essentially, if you have complementary devices, if you have a P-type for every N-type that you have, that's not much worse. I mean, if it's much worse, you can still do that, but that stage will not perform well. And sometimes you don't have the complementary device in certain processes. So what you can do, though, is that you can go from here to there. And this basically would be the same stage in terms of operation. This is still a common source, right? Because the common terminal from an AC perspective is what? This terminal, which was the same as this terminal. Because from an AC perspective, this is the same as that. These are all ground. And if you draw the small signal for them, you will get the same thing. Actually, let me just draw the small signal model for this. So the small signal model for this, you can do the T or pi. Let's do the T. It's like this. So you have Rm here. You have IE. Oh, I'm sorry, IS. I'm ignoring the channel length modulator, the body effect. IS, and then this is RD, right? And the small signal model for that was RM, IS, this is IS, RD to ground. This is V out. Look at these two. They're identical. They are the same thing. They're just drawn differently. One is the upside down version of the other one. These are the same stage, topologically. So every N-type stage you can take it and make it into a P-type stage. And every P-type stage you can convert to an N-type stage, as long as you have the complementary device. Now sometimes you may not have, is there a question? Yes.
So with the current source in the small signal,
Uh-huh.
do we always assume there's a RO
Not necessarily. So the question is that do we always assume that there's an RO in parallel with a current source? Not necessarily, but if you want to know what kind of resistance you're looking at, if you're making that before you start, you're making your circuit completely with transistors, you need to know that this is an RO type of thing. So that tells you whether or not you have to worry about it. And if it tells you, yes, no, this is a source of worry, you're still not done. We will see we can make actually better current sources that whose output resistance are higher than RO, right? We even have that topology essentially even on this whiteboard, if you want to think about it. If I want to get something higher than RO, where do you see something higher than RO in the stuff that's behind me? A cascode, right? Exactly. So these resistances are higher than RO. So you can actually, if you really want to make something that's higher output resistance, you can use one of these cascodes. Of course, there's a trade-off there. What is the trade-off? What are you losing when you use a cascode as a current source, for example, versus a single transistor? And we were going to talk about these in details, but just it's good to think about them as we go. Well, the current is going to be the same, right? Because you can just basically you're passing the same current through the same thing. It's a headroom issue again. It can't go to a low, it stops being a current source. Basically, it leaves the pinch-off region earlier. So the range of actual operation, usefulness of it, is reduced. So, but you can. So going back to your question, which is a good question, is that not necessarily. Sometimes it makes sense to think about it, say, okay, this is an ideal current source. I can just think about it, make it simple. The design process works that way. You don't want to start from the most complicated thing in the beginning. You want to start with the simplest essential element, and you want to add to it and build around it. Learning is like that. Because essentially you're designing the connection of your brains, right? You don't want to start from the most complex thing. You want to see a simple example, add a little bit more to it, add a little bit more to it, add a little bit more to it, expand on that. We don't learn by just seeing the most general case in the beginning, from the beginning. I don't think people learn that way. Yeah, sorry.
So initially, we tend to think the ideal current source as open circuit.
Yeah, you can start with that, but in the back of your head, you know that, okay, if the impedances that this is connected to are all large, then I have to worry about it. And if I have an RM, I don't have to worry about it. I don't even want to think about it. And we'll see. I mean, you will see when we need to think about that and when we won't, in many examples as we go.
What if the current source is in the current path?
Well, if your current source is in the current path, right? Let's talk about it. So this is the question. What if the current source is in the current path? If you have a current source in series with anything, what is that? A current source in series with another element that's not a current source. What is it? It's a current source. It's a current source, right? A current source, an ideal current source in series. Did I say parallel? Oh, sorry. In series with another element, right? As long as this is not another ideal current source, is exactly equivalent to the current source itself. Because the ideal current source forces the current of the branch. Right? The same way that an ideal voltage source in parallel with anything that's not an ideal voltage source is the same as that ideal voltage source.
Yeah, but when we deal with that in the small signal circuit.
In the small signal circuit, this is open. And therefore, so it's an open circuit in series with some finite impedance. What is the series combination of finite and infinity? What is finite plus infinity? Infinity. So it's open circuit.
So my transistor is open.
If your transistor is so you see, this is the question. The question you ask, which was a good question. Both of them are good questions. I'm just saying that we need to differentiate. The question you asked, what if I have a current source in series with something? I say that if you have an ideal current source, it's just a current source. Now, if this is not an ideal current source, it has some R1, then of course, then this is not equivalent to that. There's a Norton equivalent for this, which you can calculate, and it will have some finite resistance, which basically will appear when you set in a small signal. What you see is this gone. It's this plus that. right? Sure. No, I mean, these are good questions. You should keep asking them because it should make sense. This process should make sense. If it doesn't make sense, you cannot design. You're just shooting in the dark. So here's the thing. This is the folded cascode. This is an example of a two-stage, two-transistor stage, another transistor stage. So that's one example. Now, there are other stages that are of interest potentially as two-transistor stages. And we're going to talk about some. I'm going to briefly talk about them so that you mention them to you. And then we'll go and talk about perhaps the greatest of them all after the break. But before the break, let's cover some of the contenders or some of the runner-ups of these stages. And these are good things to understand, and you will have to understand why we use them and why we don't. The other thing that we've talked about, of course, is the active load. We've talked about this. You can have two drains, for example. So this is, again, we talked about this extensively. I'm just kind of like putting it there for completion. So let's say you have an N-type and a P-type transistor, NPN or PNP. You have V in, V out, and then you have some VDD. And we looked at this, and we said, OK, this is how you get gain, which is basically what we did before. But if you think about it as a two-stage transistor, two-transistor stage, you have an RON, an ROP, and then you have a drive, which basically is V in. So, and this is going to be GM V in. So if I ask you what's the gain, it's clear that it's GM times RON parallel ROP with a minus sign because the current is being pulled out of that node. So that's the voltage gain in the absence of any additional load. Right? We talked about this, and then we saw that we can cascode it. We just did that for MOSFET, and that's fine. Now, the other interesting thing is that this works if you have the complementary device, as we discussed right now, right? Now, there are some cases where you don't have a really good complementary device. For example, we have talked about the bipolar process and the CMOS process, and we've talked about them as two different worlds, right? I mean, the way we deal with them right now is that we go to the bipolar world, we deal with bipolars. We go to CMOS world, we deal with CMOS. But there are actually processes very commonly used that are called BiCMOS processes, which basically allows you to have both bipolars and CMOS on the same process. Now, some of the bipolars that are in there, actually, they're HBTs. They're silicon germanium, for example. A very common form of this thing are silicon germanium BiCMOS processes, where you get a very good, incredibly high frequency bipolar NPN, whose base is essentially made out of silicon germanium alloy. And we talked about that, how it enhances the performance of the system by improving the emitter injection efficiency and the base resistance and all those things when we were talking about the device. And you also have a complementary CMOS process. But you do not have a really good PMP. Actually, your PMP is really crummy, because it's a lateral PMP and all those things. But just like, so are we said, oh, we have this great NPN, but we don't have a good PMP at all. Our PMP's early voltage is horrible, its beta is horrible, its frequency response is horrible, all of it, everything about it is horrible. So what do we do? Are we done? Let's say we are in a BiCMOS process. Can you think of a solution? So if you could mix bipolars and CMOS transistors, can you think of something, a stage that would give you something reasonable in terms of gain? What did we use this PMP for? Why do we have this PMP instead of a resistor? We are really using it as something. As what? As a current source, right? Basically, we are using it as a high output impedance thing that can carry current. Right? So I want to replace this with something that can do that, but perhaps made out of MOSFETs. So you can make a stage that will look like this. So your drive comes from this guy. This guy, you remember, these bipolars are really good at giving you GM for a given current. Your GM is coming from this guy, because the GM of bipolars is IC over VT. And VT is a small number. This is their threshold voltage. Now, this is where it gets really messy, because you have two different VTs that are there. So V thermal. OK. Right? That's a 25 millivolts at room temperature, 25.8 millivolts. So that's you get for 1 milliamp, you get 40 millisiemens. And we did this calculation back then. You saw that you get a lot less for a MOSFET. Now, but I need high output resistance for something that can source current, right? P-type devices can source current, and N-type devices can sink current. And I'm using terminology. This is a common terminology. I throw them in because I want you to get familiar with this terminology. So they can source current, and they can sink current. I want a high impedance thing that can source current. How do we make it out of MOSFETs? What kind of MOSFET should I use? What type? N-type or P-type? P-type, right? So a P-type MOSFET here at some V bias can do that. So let's say you have a V in, and this is your V out. So here you have the RON of the bipolar. It's called the RONB, right? Which is basically early voltage divided. Let's say this is running at 1 milliamp, right? This is going to be about 100 kilo ohm. Then you have ROP of the MOSFET. That probably is going to be lower than what you get from this, unless you make it large. Or you could basically either make the L large here, because you have control over W over L, or if you don't want to do that, you say, oh, that gives me too much capacitance here, etc. For some reason, I don't want to deal with that. Then I can cascode it. And instead, I will get ROMP times GMP ROPM, right? And my gain, again, is going to be V in here. That's the drive, GMN B, did we say B? Yeah, for bipolar. And then V in times the parallel combination of these resistors. So you can see there's nothing magical about any of these things if you understand. It's just a question of impedances and drivers. A lot of circuit design really is understanding the drive capability and the impedance that you drive. And when we get to higher frequency, we'll see it also becomes a question of time constants and transfer constants. Right? You can distill it to some essence of this thing. But so anyway, so those kind of things are possible. You can actually have combination of these things. Now another stage. Any questions on this? Any more suggestions? Anything you? Circuit design is kind of like drawing or painting. It's unbounded. You can actually put things any way you want, and everyone has a style eventually. You will see. And if you look at people who have been designing circuits, I mean, sometimes I look at some circuits and say, well, this must have been designed by such and such. People who have developed their style after a while. This must be the work of such and such. And it is kind of like that, because there are infinite possibilities. There are many different ways to do the same thing, which is actually the beauty of it. There's not one single solution to the problem. But anyway, so another stage, another combination of two transistors is the so-called Darlington. And this is used almost exclusively in bipolars, and you will see why. The Darlington combination is basically having a transistor, the emitter of one transistor driving the base of the second transistor, and they share the same collector current. So it's a compound transistor, if you will. Something like that. So you can like this, call this Q1 and Q2. Now, what does this compound transistor do? What is the purpose of this thing? What do you think the purpose of this something like this would be? Increase the gain. Yes, what gain? Current gain, right? Why? Because if this current is IB, let's call it IB1, this current, which is basically IE1, is going to be beta plus 1, well, practically beta, but which is the same thing as beta plus 1 as far as I'm concerned, times that. But just let's write it precisely and uselessly as this. Well, should write it the other way around. Anyway, so let's keep it that way. And then this current is going to get multiplied by another beta, So this current is going to be beta times beta plus 1 IB1. And this current was beta IB1. Assuming that the beta for both transistors is the same, which may not be the case, even if there are similar transistors. And I'll ask you why in a few seconds. Just think about it. But then the total current here is basically what? It's beta times beta plus 2 IB1. It basically essentially is beta squared IB1. Right? I personally think that some of the beta plus 2s and beta plus 1s are a little bit ridiculous. But you see them everywhere, so you need to understand. And sometimes it matters because if you subtract 2 of them, then that 1 matters. But here, so it's basically a transistor. So if you think about this, if I put this inside a black box, right, and sell it to you, say, this is the base, this is the collector, this is the emitter. What does this transistor, how does this new compound transistor behave? What is the beta of this compound transistor? Beta squared. So this is a very high beta transistor. Like you get a beta of 10,000, 5,000. So wow, this is a really high beta transistor. So well, great. We can increase our current gain. We can increase our beta significantly. What's the drawback of this thing? Can you point out a drawback or drawbacks? You have to have a really high input impedance. You mean for the driver?
Well, yeah, well, if
You're driving, so you see a very high input impedance. But that's not necessarily a bad thing. I mean, it could be a bad thing. But this terminal, so let's calculate what that input impedance is. That's a good question, right? So let's say, if I calculate, let's calculate this input impedance, roughly. What do you see? I mean, we know the trick for this. We know that, you remember the reflection rule? We said if you have something in the emitter, you can bring it to the base, looked at it from the base, is beta plus times whatever it is in the emitter, which is beta essentially times the emitter. And if you take something from the base and move it to the emitter, you divide it by beta plus 1, or beta. Okay? So here, what do I see looking, if this was grounded, for the sake of argument, what is the resistance looking into the base here? So this is R pi 2, right? Now, therefore, what did I see here? I see the R pi times R pi 1 plus beta plus 1 R pi 2. What is that like? Well, it looks like this. But let's think about it a little bit more carefully. Because what is R pi? R pi, isn't R pi beta Rm, or beta over Gm? Therefore, it's beta Vt over Ic. Do these two transistors have the same beta? It's the same Ic? No. This Ic is beta times roughly larger than this Ic. So this R pi is beta times smaller than this R pi. I'm sorry, beta times smaller than this R pi. So what do you roughly get? So let's say if this R pi, let's call this Rm. So let's call this R pi of the compound transistor. So this is Rm, which is the Gm of this big transistor. So R pi 2 is this, but R pi 1 related to R pi 2 is going to be beta times larger. So you get a beta R pi 2 plus beta plus 1 R pi 2, which is roughly saying it's 2 beta R pi 2, which basically is saying it's 2 beta squared Rm2, which is roughly 1 over Gm of the total transistor, because most of the current is carried by this guy. So you see a larger input resistance too, as you pointed out. Now that may be a good thing or a bad thing, depending on what you're trying to do. If you're trying to make a voltage sensor, voltmeter, it's a good thing. You're making a better voltmeter because your input impedance is going up. That's actually one of the reasons that this stage would be used. You get a high beta, fine. You reduce this base current, but there's a price to be paid because this guy is not operating at the same current, and that's why sometimes you add a current source here. in between to adjust for that. And we can talk about that. But the other question I have for you is that now, what is the overall GM of this device? Or let me ask you this question. From a practical perspective, is it as easy to use as a single transistor? We'll get to the GM question in a second. So this has nothing to do with the GM. What I'm asking. Do you see another drawback? Yes?
You need more voltage before it bias both.
Exactly. You need more voltage. Very good. You need a lot. You need if you need a 0.7 volt to turn one on roughly. Now you need 1.4 volts. So you need a lot more voltage. So if you're operating in low voltage operations, this is not your cup of tea. This is not what you want. And that's why nowadays you only see these kind of things in power devices, power electronic things that work with relatively high voltages and things of that sort. So this stage has some benefits and advantages and disadvantages, but it's overall something that's to be aware of. It's called Darlington stage, and there are variations on that. And that's essentially for that. There's another two-transistor stage that, again, we will talk about more extensively later, but I want us to be familiar with it, at least at some level. And that's the so-called current mirror. Again, we'll talk about these a lot, and we'll use them a lot. So this is something we use extensively. So the sooner we get familiar with them, the better. The idea of a current mirror is that if you think about a transistor to the first order, like a BJT or MOSFET, what determines its collector current or its drain current? What is the number one variable that determines the collector or drain current? Base emitter voltage or gate source voltage, right? So if two transistors have the same base emitter voltage or gate source voltage, you would expect them to have more or less the same current if they're both in the same region of operation, right? If they're both in pinch-off. So that's the basic principle of a current mirror. If you want to copy a current, if you want to reflect a current somewhere else, you want to create two transistors that share the same base emitter or gate source voltage. So for example, you can make something like this. And again, like I said, if we talk about these in a lot more detail as we go soon, but it's good to understand it as a two-transistor stage. So you have two things that have share the same current. Basically, these are connected, right? I mean, we don't show this connection often, but they have the same VGS. So the VGS of this one and VGS of that one are the same. So if this current is ID, and if there were no channel length modulation, let's say lambda was 0, or saying, which is equivalent to saying VA was infinity, if they have the same VGS, they should carry the same current, because the current in the pinch-off region, as long as they're in pinch-off region, is mu n Cox over 2 W over L VGS minus VT squared, right? So ID1 and ID2 are going to be the same because they have the same, let's go W1, W over L, W over L, M2, and M1. So they're sharing the same VGS. So does it mean that if I put a current source here and force a current source I1, and I have a way of maintaining this in saturation, which means that I have to connect it to some voltage, this current would be I1, right? Is that correct? So it seems that you can reflect this current from here to there. Does this stage work the way I've drawn it? Or is there a problem with it? Do you see a problem? Do you see any problems with this stage, the way I've drawn it? Let me ask you a question. What determines the potential of this node? The DC potential of this node? What VGS actually is, the value of VGS? The amount of charge on the gate, right? So, but that's not exactly the amount of charge on the gate. So this is like a floating node with two capacitors. So this is like basically a capacitor here connected to another capacitor here to ground, to whatever, some voltage, right? To ground. It's like asking what's the voltage on this node? It could be anything, right? So there's a problem. This gate is floating the same way that this is floating. It's called the floating gate. It's not forced to have, so if you have some stored charge in there, it can have some any arbitrary value, so you can get some unpredictable behavior. You need to make sure that this gate has some fixed value. Now, in the case of a classic MOSFET, you're not carrying any gate current, so that's not a problem. In the case of a bipolar, there would be even a bigger problem, because both of these want to have current going into them, and this current has to come from somewhere, and it can't come out of the thin air. Right? So there needs to be some connection to this gate. Now, we do it by doing this. We connect it to this side, which is the reference side, and that way we keep the drain of this guy separated from its gate, so we maintain a high impedance here. But by doing so, we create a pathway for charge and for charging and discharging of this node, so you keep these two on the same level. And by the way, this also guarantees that if your threshold is positive, the transistor will never enter triode region. It will either be in pinch off or off. So when you feed this current, now in the case of a MOSFET, there will be no current flowing through here. No DC current in the classic MOSFET sense. And if there is a bipolar, some of that current is actually supplied through here, some of that base current. So this is what we call a current mirror. It copies a current. Now, the beauty of current mirror, and we'll use them extensively, is that you can copy it more than once. You can, if I take this node and connect it to another transistor, with this W over L, I can make another copy of this current. I can make multiple copies of this thing. So if I have one good reference, which we'll talk about later, much later, about how we generate these really good references, you can copy it as many times as you want. And not only you can do that, what happens if I make this W 2W with respect to that? What would that current be? It would be twice as large, right? It's basically like saying, oh, I make two of them with W over L. And that's probably a better way of doing it than the way I just drew, for reasons that we'll discuss later, for matching and all those things. That current would be 2ID1. You can make it any ratio, essentially, by controlling these things. So this current mirror core concept is very important. And we'll use it extensively. And again, of course, like any other stage, it can be flipped upside down. Right? It can be inverted. So what's the inverted version of this thing look like? The inverted version of this thing looks like this. Now, there's a difference between these, right? This is a current source that does what? Source or sink current? It can sink current, right? So an N-type current source can sink current. And a P-type current source can source current. So if you needed to source current, you can use a P-type current source. If you needed to sink current, you can use an N-type current source. Now, let's say, if you say, well, wait a second, but this way, you really need two of these good references. Right? Do I? Or can I make this off of this too? Can you suggest a solution? There are more than one solution. But let's say you have already this one, and I don't want to make another copy of it. I just want to use that good current source that I've worked really hard to make a good reference current source, and I want to use it somewhere else. How do I do that? Any suggestions? Yes?
Just combine it with the NMOS underneath your BiCMOS.
Yeah, so you can make another branch of this. Right, you already have this. You can make another copy of that current source and put it here. Because now this is playing the role of that current source that was there. This is used so extensively that sometimes you actually have a shorthand notation for this. So you may see something like this. Mirrors. Right? So I think that's a shorthand notation for everything other than this part. I didn't copy that part. Well, If I wanted to do that, then it would be 1 here and a double here. Right? So that's the shorthand notation for this. Does it make sense to you? But remember, whatever you do, you need to have the gates that are connected to each other biased somehow, or the base is connected somehow. Anyway, so that was some of the review of some of the basic two transistor stages. Sorry?
There's more ways to do that?
More ways? Yeah, there are lots of ways to do that. We'll talk about it. We'll have more detailed discussions of this later. But yeah, there are lots of ways to play this game. Yeah. This is the most common, this is the most standard way of doing it. Any other questions? All right, so after the break, we'll talk about the greatest of the two transistor stages.